Can I start now? Okay. Well, fantastic. So thanks, Adam, for this wonderful introduction. Yes, indeed, I'm full-time based here in Warsaw since the 1st of July, and just maybe a little bit of introduction. So I came here for the first time about a year and a half ago, and I gave a talk about self-testing, and then when Adam asked me to give a talk again, well, since I still work on self-testing, I was I wasn't sure what to do, so I decided to give a self-testing talk, but focusing on the recent developments. Okay, so that's the second part of the title. I guess if somebody has been to the previous talk, maybe the first 25-30% will be similar, but then I'm going to show some new results. So hopefully this should be exciting. Okay, so the outline of the talk, self-testing is inherently linked to Bell non-locality, to the phenomenon of quantum system exhibiting non-classical correlations. So I'll have to mention that at the beginning. And then I'm going to tell you what actually is the idea of self-testing. So this will be kind of the standard results. And then I have two sections about the recent developments. So this is the weak self-testing and self-testing of entangled measurements. And then at the end, there's going to be a brief summary. And of course, if there are any questions, I'm very happy to take them either during the talk or afterwards. Okay, so non-locality. So we are in the typical Bell scenario. We have two devices or two quantum systems. We can perform different measurements on them. The choice of measurements is given by X and Y. The measurement outcomes are given by A and B. And we really don't know much about these devices. The only thing that we can do is to choose settings, observe the outcomes. We assume that the devices behave, every time we test them, they behave in the same way, which means that this probability distribution is somehow well-defined. Okay, we can just repeat the experiment many times and collect statistics to estimate this. And since we are interested in the fundamental features, we kind of assume that this estimation can be done to arbitrary precision. Okay, so in the end, we can really assume that we have access precisely to this distribution. And okay, and then there is this notion of what it means for correlations to be local or classical, and this essentially means that I can write my correlations as a convex combination. Okay, so this is this lambda of product terms. Okay, so you can think that these QA and QB, these are some kind of local response functions of the two devices. So they depend on the local input and the shared randomness. And you produce some local output, and then you take convex combination, okay? And this is a well agreed upon definition of what it means for the devices to behave classically, okay? And we kind of think that, classical systems, this is what they are able to do in terms of correlations that they can produce. So if you can write your distribution like this, then we say it's local, and if you cannot, then we say it's non-local in the sense of Bell, or equivalently that it violates some Bell inequality. And then there is this very simple observation that if my state is separable, okay, so now I'm talking about quantum states, if I can write my bipartite state as a convex combination of product states, then I know that the statistics will be local. And this is essentially because whatever measurements, so these are my measurements that I choose to perform on my state, because the state kind of factorizes inside, well, this gives rise to these local response functions, okay? So if I have a state, if I find a separable decomposition of the state, then automatically I'm guaranteed that all the statistics that come out of this state are local. So if the state is separable, statistics are local, and then you can kind of take the contrapositive. So if you observe non-local statistics, then you can really deduce, okay, well, my state is entangled, okay? So this is very nice, and it's been known for a long time. But of course, you can ask, well, okay, can I make any more refined statements, okay? And I guess, at least from my point of view, the answer to this is self-testing, okay? It's maybe not the only answer, but it's the one that I care about. So what is self-testing? Well, the abstract mathematical formulation of the task is actually very simple. So I'm given a probability distribution, okay? And I'm promised that this is a quantum probability distribution. So it really comes from measuring some particular quantum state using some particular quantum measurements. And then the goal is just to deduce something about the state or the measurements, okay? And as I said, this is inherently connected with non-locality because in the end, we want to deduce some quantum features of this state or of these measurements. And since non-locality is, you know, one way of certifying that something is indeed non-local is by violating Bell inequalities. So then very often, instead of making this statement kind of giving access to the entire distribution, I'm just going to say, look, I have violated some Bell inequality, okay? For those that are not fully familiar with this, a Bell inequality or Bell functional is just a linear combination of my probability terms, and it kind of makes it easy because, you know, I can just compute, this is just a number, and if this number is bigger than what we call the classical threshold of the inequality, then I say, well, I violated this Bell inequality, so there must be something quantum happening in my system, okay? So, so you can just make a self-testing statement based entirely on this single number, which you compute from your experimental statistics. And what is kind of interesting is that in some cases where these correlations are particularly strong, this characterization is essentially complete, okay? And now I'm just going to give you an example of what it means. But before I go to this, I have to just tell you a little bit about what is a quantum measurement, just or like how I like to describe them, okay? So for me, a quantum measurement is just a resolution of the identity into positive semi-definite operators, where each operator is kind of corresponds to a particular outcome of the measurement, okay? And for instance, if I have a measurement with two outcomes, which essentially corresponds to two operators, F0 and F1, which add to identity and they are positive semi-definite, I can equivalently write it as an observable, okay? So this is just, I guess for people with physics background, this is a kind of a natural thing that maybe you want to measure in an experiment, but you can really just think of this as some kind of like mathematical mapping between these two operators into a single operator, and this mapping is one-to-one. So if I give you a Hermitian operator which is between minus identity and identity, well, this is a valid measurement, okay? And it's kind of clear that if I start from a valid measurement, I will get a Hermitian operator which satisfies this, okay? So it's just an equivalent of describing it, which makes it easy for me to show you the example. And the example is the famous CHSH inequality. So this is kind of the simplest and the most well-known Bell inequality. Okay, so in this slide, so I have the beta is my kind of Bell value. So this is the number I'm computing. This is my state. Okay, W is the Bell operator. Okay, so in some sense, this corresponds to, this tells me, okay, what kind of linear combination of probabilities I have to take to compute my value. In this setup, Alice and Bob have, so A and B, Alice and Bob, the two boxes, they have two choices of inputs, okay? So the subscript here corresponds to the choice of input, so this is the 0th input of Alice, this is the first one, and similarly for Bob. And they have two outcomes as presented on the previous slide, so there is kind of one outcome which corresponds to +1 eigenvalue and the other outcome which corresponds to -1 eigenvalue. And essentially, you know, I just, so Alice and Bob choose measurements, I construct this operator, I compute the trace with the state, and I have a look at the number, okay? And it's known that if what Alice and Bob are doing is somehow classical, and you know, your definition of classicality, like you can kind of choose whatever you want, but you can, for example, say, well, I say that the measurements, the local measurements, so let's say A0 and A1, they have to commute, okay? They have to be diagonal in the same basis. Well, if they commute, then the largest number you can get is 2, okay? Whereas if you drop that classicality restriction, if you say, well, they can do anything that quantum mechanics allows them to do, then actually you can go all the way to 2√2, okay? And a particular way of doing this is by sharing the maximally entangled state of 2 qubits, okay? And then performing these kind of, so these are just the Pauli matrices, okay? So we're performing these kind of maximally incompatible measurements on each side. And I'm gonna call this particular realization, so this state and this set of measurements, the canonical realization of this probability distribution. And what is kind of interesting is that, so we say that CHSH is a self-test, which means that every realization that achieves this maximum value of 2√2 is essentially the canonical one, okay? And when I say essentially, well, let me just explain what I mean. So of course you might kind of, just want to say, well, then the state really must be a singlet and the measurements really must correspond to these Paulis, but there are two kind of inherent limitations that you cannot remove. and they are kind of very natural. I mean, the first limitation is that, well, if my state has some auxiliary degrees of freedom that my measurements kind of act trivially on, well, this is something that I can never rule out, okay? But this is somehow not that from the, let's say, from the physics point of view, this is very natural. I mean, whatever system we study, it always has an infinite number of degrees of freedom. And then, well, we can only describe the ones that we care about, okay? So in some sense, this is just saying, well, there will be degrees of freedom that do not play an active role in my experiment. I don't care about them, but nevertheless, I must kind of account for them, okay? I don't know what it is, but it might be there, okay? So this is one limitation. And the other limitation is that I cannot see local unitaries, okay? So if I apply the same unitary to the measurement, so I have some local unitary on Alice and local unitary on Bob. If I apply the same unitary to the local measurements and then the combined unitary to my state, well, of course, the statistics remain unchanged, but in some sense, my realization looks a bit different now, right? So these are the two limitations, but otherwise, that's it, okay? So basically, every quantum realization that achieves the maximum value must be of this form, where the only unknown elements are, you know, this auxiliary state and these local unitaries. Correct, yes. Okay, so I guess, okay, you're asking about the labeling of the registers. Is that?
About the position of ones in
oh, yeah.
I would guess the definition of P, I would rather put 1 times.
Well, but in the definition of the state, I have A prime, B prime. I mean, it's, okay, so just, so look, so this is A prime register. This is A double prime register. This is B prime register. This is B. I don't think, you know, since you kind of wanna.
Sure, okay, no, but it's confusing because the symbol of tensor product in the line UA times UB is not the same partition as below. So for unexperienced reader, it's difficult. That's true. But for experienced reader, it's clear.
Okay, but do you think there's a better way of writing it?
To understand correctly.
Yeah, okay.
Yeah,
So for
and luckily.
laymen are not supposed to do anything.
Yeah, and luckily this room is full of experts, but I actually don't think there is a better way of writing this, because you want A prime and B prime to be next to each other, and you also want these guys, so.
Okay, but we can think of it.
Yeah, I hope we can cope with that. So okay, so we say CHSH is a self-test, or CHSH is a rigid inequality, okay? And let me just compare it with some other kinds of statements that people make. So sometimes people prove results of the type, well, if I see some correlations, for example, the ones maximally violating, then I conclude that the entanglement of my state is lower bounded by some number, okay? And here, the measure of entanglement you choose, there are different statements that people prove, okay? So this would be like, okay, certifying entanglement based on correlations, okay, good. But note that what I'm saying is a bit stronger. So I say, well, if you see these correlations, then my state must contain a particular state, okay? In this case, the maximally entangled state of 2 qubits, okay? So I would call this device-independent entanglement certification, whereas this is kind of self-testing, okay? And to me, self-testing is like a deluxe version of this device-independent entanglement certification, because I don't just know how much entanglement there is, I know exactly what kind of entanglement there is, okay? So I get more information than in the first case.
But this contain is quite general. It could be any combination that includes this, right?
Okay, but if you want, okay, so just to, you know, if you want.
That means that the coefficient is non-zero that comes with.
Oh no. Okay, so okay. Okay, so contain means, so if you look at the form of this state, basically I say, well, I don't know what my boxes are doing, but what I do know is that there exists some kind of local processing, so I can apply some local channel on one box, some local channel on the other box, such that I obtain this singlet, and it's a perfect singlet. Okay, so this is what I mean it contains. So it's not just sometimes it works, sometimes it doesn't. Like if I do the right channels.
But mathematically, you have a density matrix for OAB.
Yeah.
Now, what does it contain in terms of the density?
So there exist local extraction channels which out of density...
Mathematics doesn't know about this.
Oh, of course it does.
What? You have a density matrix, which is an operator.
Sorry. Oh, in terms of operators. Okay, so I agree.
Compose the row into its components
Yeah.
with some coefficients lambda.
Yeah.
And what does it mean contain?
Okay, so I agree that it's not easy to verify. So if I give you a state and I ask, oh, does it contain a singlet or not? I don't know of an efficient way of verifying it.
No, I'm not talking about verifying, but the definition.
Oh, the definition is fine.
Definition
No,
containing.
if there exist extraction channels that produce a singlet. Oh, but this is a valid this is a valid mathematical definition.
The row
The
is
point is, Jędrzej, that probably some people do not know what is extraction.
Oh, just a local. Okay, so I mean,
If you explain
yeah.
this,
Oh, sorry.
it will be clear.
That's what was my comment.
No chalk today. Oh, fantastic. Okay, so what is a quantum channel? So suppose that I have two. So I have some Hilbert space A, and I have some Hilbert space B, and a channel is just a. Let me just write this. Okay, a channel is just a completely positive trace-preserving map that acts linear operators acting on HA to linear operators acting on HB. In my case, the input Hilbert space, I don't know, okay? This is kind of fixed by my state, and it could be anything. The output is just a qubit, okay? And now I'm gonna require that there exist two channels, one acting on A and another acting on B, such that if I apply them to my unknown state, I'm gonna get a perfect singlet. So yeah? Okay. So this is what it means that it contains a singlet, because in some sense, operationally, if I just locally act on it, I can retrieve such a singlet, okay? So this is like a resource for whatever I wanna do. And from the more philosophical point of view, self-testing provides a very nice connection between, let's say, the abstract formalism in terms of these Hilbert spaces and operators acting on them, and the statistics that we can see in an experiment, okay? So for me, it's a very nice connection between like the abstract formalism and what we can really see in an experiment. All right. Self-testing also has implications on the geometry of the quantum set, okay? So the quantum set of correlations, it's just, you should really think that, I just collect all kinds of statistics I can get from measuring quantum systems, okay? So this is shown by this kind of semicircle here. The local set is the kind of correlations I can achieve from classical systems, okay? And it's known that the local set is strictly contained inside the quantum set. And one thing that self-testing tells us is that in this slice, if I plot the CHSH inequality, well, this is the classical value, okay? This is kind of where the local set ends. Whereas this is the quantum value, the maximum. And self-testing tells us that there's just a single point in the quantum set that achieves this value, okay? So this has a unique maximizer. Whereas, you might ask, okay, is it always the case? And it turns out that this is not always the case, because there are inequalities for which the quantum value is achieved by more than a single point, okay? And of course, if you don't have a unique maximizer, you cannot hope for the rigidity statement of the usual kind, of the one I presented to you, okay? Okay, so self-testing has been shown for many, let's say, Bell inequalities, for example, the CHSH, that's the one I presented, and then there are kind of variants of CHSH, the tilted, the biased, there are chained Bell inequalities. It has also been shown for multipartite inequalities, like the Mermin inequality and the MABK family, and also some more games. So in some sense, you might think, okay, now we have a collection of these self-testing results. Well, what's next then? What are the new interesting things you can still prove? And this is when it comes to the recent developments, okay? And of course, I have to warn you that the choice I've made is somehow arbitrary, and it's affected by my own interests, okay? So today I will present just two recent developments, okay? The first one is tries to answer the question of whether self-testing is a generic phenomenon, okay? Whether, if I just take a Bell inequality, is it always a self-test or is it not? Okay, and I'll briefly comment on that. Whereas the second one is trying to take this paradigm a bit further and say, well, so far we've been self-testing states and measurements. Can we self-test more complex objects? For example, entangled measurements, okay? And of course, there is actually many developments in this field, and I will not mention these in the talk, but it turns out that you can also self-test quantum channels. You can also self-test in prepare and measure scenarios. So these are the so-called quantum random access codes. And now let me advertise that there will be a seminar in 2 weeks by Mate Farkas from Gdańsk, precisely about this. And of course, from the experimental point of view, can you make these statements robust? Okay, because so far I've just told you, well, if you see the exact maximum, you know what's happening. But what if you see, instead of 2 root 2, you see 2.7 or 2.4 or 2.3, can you still make a meaningful statement? So this is basically what I kind of mentioned at my last seminar. I think it's a very interesting question, but I guess today, I will not have time to talk about this. Okay, so the first one is this kind of weak self-testing. So the quantum set of correlations is just a convex body, okay? We don't actually know that much about this. It has some kind of flat edges and it has some curved edges, and it's known that, or it's kind of easy to intuitively see that if I want my correlation, so the statistics, to like uniquely determine the state and the measurements that I'm doing, it has to be in some sense extremal, okay? And extremal, in fact, it turns out just in the kind of geometric sense that, well, I cannot decompose that statistics as a convex combination of some other points in the set, okay? So for example, for this set, the extremal points just correspond, okay, so we have the 2 vertices here. These are, let's say, not interesting because maybe they correspond to the deterministic vertices, okay? So this is basically classical statistics that we're not interested in. But then there are these kind of curved extremal points, or whole families of extremal points, and maybe they are actually self-test, okay? Maybe they really can be achieved in an essentially unique way. And I guess one of the big questions that I think is important for the field is, well, is every extremal non-local point a self-test, okay? Because this would really show that all the extremal correlations can be achieved in a unique way, and this is an interesting way of certifying things. But this turns out to be a hard question, so we don't really actually know what the answer to this is. So you can switch gears and you say, well, okay, what about Bell inequalities, okay? Is every Bell inequality a self-test? And
sorry, just a short question.
Yeah.
So here somehow you assume that the symmetry is broken, somehow the beta goes up, so the classical case will be down.
Okay, so I haven't drawn the classical set here because
No, but in the statement, the extremal points are not so interesting.
Sorry, but
assume that the lower part corresponds to the classical, because you can ask whether possibly up there could be also a single point which is extremal.
It could be.
Exclude a priori such a.
You're right, and
But before I'm saying up or down, I'm asking whether this picture has already some symmetries broken or not yet.
This is just I just decided to draw an arbitrary convex set.
So therefore, then we cannot a priori say that the small dots points are not interesting for us, because it may happen there. You will have extremum for such a point.
You're right. Yeah. So I guess since I haven't drawn the local set, indeed these could be. And I think actually, yeah, but I think actually you're right, and probably okay, because this quantum set is a convex body in high-dimensional space. So in fact,
I understand that there is only a symbolic.
Yeah. So the only statement was that those points could also be of interest, possible.
They could be, and indeed it turns out that, and of course, if I want to plot something, I can only plot in 2 dimensions and maybe 3 dimensions, and of course then you basically. You can, I don't know, plot a cross section through the set, or you can plot a projection on some variables, and then indeed the shapes you can get can be very counterintuitive. So you're right. So okay, I guess what I wanted to say is like if these correspond to local points, then they are not interesting from the self-testing, but indeed there could be. Okay, so the question is every non-trivial Bell inequality a self-test? And by non-trivial, I just mean, well, I want something that can be violated by quantum mechanics. Okay, so the quantum value should be strictly more than classical, so that I can really certify, I can really see some quantumness in my system. And of course you say no, because there exist these inequalities for which there is more than one maximizer. There is a whole line of maximizers. And this already tells you that the usual self-testing statement will not hold in this case, okay? But actually when you look at, okay, so this is now talking about a particular example that we have found at some point. You look at this line and you realize, well, actually, all these points, okay, they can be achieved with a single state, okay? So it's always the singlet that we're measuring, and in order to move on this line, you just have to kind of slightly adapt your measurements, okay? There's like a one-parameter family of settings on Alice and settings on Bob, and if you go through this one-parameter family, you go on this line, okay? So you might say, well, maybe, although I cannot fully determine the system, maybe at least I can certify the state, okay? And this turns out to be true, okay? So we can now prove that if you see the maximum violation, you really have this state, okay? So state certification remains as before, except that you cannot fully determine the measurements, okay? And in fact, even if I gave you full statistics, so I tell you exactly where on this line you are, you cannot fully characterize the measurements unless you happen to be at the endpoints, okay? Somehow the endpoints are special, and then we have the standard self-testing statement, but if you're somewhere in the middle, it's not really clear what you can say, okay? Interestingly, you can still certify local randomness, okay? Which means that, well, if I see this maximum violation, then I can guarantee that the local measurement outcomes, they are maximally random and they are unknown to any external eavesdroppers, okay? And this is something that people use in let's say, device-independent cryptography. When Alice and Bob share some devices, they don't really know where they came from, and they could have been produced by the eavesdropper. And then what they will do, they will just use these devices to violate some Bell inequality, and from this they will try to deduce, okay, I don't know what these devices are doing, but I can guarantee that they are producing some randomness, which is unknown to this third party. And indeed, for the case of this inequality, this still works, okay? So even though you don't know exactly what the measurements are, you can still certify randomness, which is kind of interesting. And the last implication of this kind of what I call weak self-testing statement is that there are indeed no other points of the quantum set which maximally violate this Bell inequality. So in some sense, this picture is accurate, okay? There is just a single line segment which gives me the maximum violation, and there is no other ways of doing this, okay? So this is weak self-testing. And of course now one would like to kind of push this further and maybe find more striking counterexamples, okay? So one interesting thing would be to find a Bell inequality which is violated by genuinely different states, okay? And this one, in the bipartite case, we don't have. In the tripartite case, actually they exist, and so we can come up with some pretty natural Bell inequalities such that the maximum violation doesn't even tell you what entanglement class you are in, okay? So in fact, it can be achieved either just using bipartite entanglement between Alice and Bob and Charlie being classically correlated, but it can also be achieved by some kind of GHZ state, okay? So it seems that in the multipartite case, the power of self-testing is significantly limited, okay? And I guess, of course, if we realize that, okay, such counterexamples exist, well, the right question to ask is, well, can I still deduce something, okay? Are there any meaningful statements, self-testing statements I can still make? And I guess at this point, this is really not clear, okay? So we know these counterexamples, but we don't know what could still be deduced in those cases. Okay, so this is the first recent development. And I guess the other recent development is self-testing of entangled measurements. And before I go directly to the entangled measurement, let me just tell you very briefly about quantum networks, okay, which is a very popular topic these days. So a quantum network is, just as you might imagine, is just a network of nodes. And I guess the feature of what makes it a network is that although everything is connected, not everything has direct connections, okay? So just think, like a non-trivial network. So just think of a case where you have like three parties, Alice, Bob, and Charlie, but there's only two sources in the network, okay? And these are bipartite sources. So there's one source that distributes a state to Alice and Bob.
It's extremely impolite to ask the question, what do you mean by connecting?
Okay, no, it's extremely polite actually. So when I say connected, I really mean, I say two nodes are connected if there exists a source that is capable of emitting a bipartite state, such that the first share goes to 1 and the second share goes to. So essentially these parties kind of for free are allowed to generate bipartite states. That's just what I mean by connected. And you know, physically it means that there is a quantum channel between them.
Then A would be at B with C, and E with A with C is connected through the...
Exactly. So in this case, I would say, well, these are connected, but A and C are not quite connected. Not yet, okay?
Is it this weak connection?
So far there is no weak connection. No, so I guess,
If I would have, I mean, that doesn't stop on 3 nodes, as you can.
no, of course not.
You can have a many of them.
You can have a lot of nodes indeed, yes. I mean, no, from the like, suppose you want to,
Anyway, this connection means that they are only nearest neighbors. are connected.
well, nearest,
Sense.
okay, nearest,
They
no.
can be reached by the same devices and
I mean, nearest neighbors, you know, it's not really, well, I mean,
they
it's,
are connected by this device.
exactly. So,
That's the distance.
yeah, so just think in the, you know, in a real physical scenario, you have some local devices in the labs, and then in between some of the labs, you have a quantum channel, like a fiber optics cable, you can send states, okay? That means they are connected, but maybe not all nodes are connected by these channels, so then, okay, what can you do? So exactly, so this is a quantum network, and then a very natural question is, well, using such a setup, can I still distribute entanglement between A and C, okay, which are initially not connected? And the answer turns out to be yes. It's very well known. It's been discovered many, many years ago. And the device is called quantum repeater, okay? And quantum repeater relies on the phenomenon which is called entanglement swapping, okay? And entanglement swapping, what we need to kind of understand this or explain this is actually very simple. All you need is, so we have this maximally entangled state of 2 qubits that I have already shown you. And in fact, you can find 3 other states which are maximally entangled, and together they form a basis on the space of 2 qubits, okay? And then what you can ask these guys to do is to, you know, just generate the maximally entangled state, let's say the standard one, okay, and distribute it. And then I will just ask Bob, who now receives 2 qubits, to perform what we call a Bell state measurement, okay? So it's essentially a projective measurement in the basis of these 4 maximally entangled states, okay? Bob fully measures his system, he receives an outcome, okay? I'm gonna call it R. It's very easy to see that the probability of, so there's 4 possible values, okay? 1, 2, 3, 4, yes? The probability of each outcome is 1/4, okay? But what is, and after the measurement, Bob has no more quantum system anymore. But what is cool is that conditioned on a particular value of R, the state that Alice and Charlie share corresponds to one of these 4 Bell states, okay? So in some sense, okay, whatever the outcome is, they will have some maximally entangled state. They don't know which one it is, okay? So somehow if Bob like disappeared and forgot about R, well, this would not be very useful for Alice and Charlie, because without this extra classical piece of information, it's not so useful. But if he communicates it to one of them, they can apply a local unitary to bring their state back to, let's say, the usual maximally entangled state, okay? So this allows us to distribute entanglement in the network, even though Alice and Charlie have no direct connection. Just by doing this simple trick, they can establish entanglement. This is called entanglement swapping, and you know, the devices that do these things are called quantum repeaters. So in this case, we would say that Bob is actually a quantum repeater. Okay. Okay, and you know, if you look at this network, there are essentially 2 components of this network. There is the sources, okay, which just emit bipartite states, and then there is the measurement device, which performs an entangled measurement, and we already know how to certify the sources, so, well, can we also certify the entangled measurements in our self-testing framework? And now, I guess you would have to ask, okay, what does it mean to certify a measurement, okay, or even more an entangled measurement. How much time do I have actually? 15 minutes. Okay, so that should be fine. So, okay, so just kind of briefly, I would like to explain to you the idea of what it means that one measurement, that the real measurement is is certified as the ideal measurement. Okay, so suppose we have two outcome measurements. Okay, so these just correspond to a collection of positive semi-definite operators which add up to identity, and I will have two such measurements. One of them is the ideal measurement, so that's the one I'm trying to certify, and let me assume that it's projective, and I know that it acts on a particular Hilbert space. Okay, so I know the dimension. This is just for a single party. Okay, I will make it bipartite in a later slide. Whereas on the other hand, I have an unknown measurement. So this is the real one. This is the one I have in my system. Okay, and I really don't know anything about this. I don't even know what is the dimension on which it acts. Okay, and then, well, if I just know something about the statistics produced by F, what can I try to deduce about this F measurement? And it turns out it's not hard to see that kind of the best you can hope for is that F is capable of simulating the ideal one, okay? And kind of capable of simulating really means that F is at least as powerful as the original one. It could be more powerful, okay? Because in some sense with these unknown devices, just like I showed you before, there is never a way of giving an upper limit of their power, okay? Then they can be much more powerful than what they demonstrate to you, but you can put lower limits, okay? So you can put lower bounds on what they can do. And in this case, you can say, well, I don't know what F is, but it's certainly capable of simulating P. And now you can ask, well, what does it mean to simulate P? And I guess operationally, what I want to do, I want, for some unknown state rho, arbitrary state, I want to put it through a measurement device P, and I want to get some outcome X, okay? Well, unfortunately, I don't have P, I only have F, okay? And the worst thing is that this F, I don't even know what space it acts on, okay? So I cannot just feed rho into F, but I'm gonna say, look, I just want that there exists some generic pre-processing, okay? So lambda is some kind of quantum channel which prepares my rho so that I can put it into F.
There's something I don't understand.
Yeah.
The physical systems may have many degrees of freedom.
Correct.
Many physical properties, right? And these measurements of P measure one physical.
Correct.
And the F measures completely different. For example, I have a piece of kitchen salt.
Kitchen salt.
And the P measures the length of the cell units of the bond, right? It's a measurement. It should be described like this theory.
I don't think it is. Yes, okay. I think maybe we can take this offline. I think this is not a relevant question.
Then F measures the weight
Okay.
of the crystal. Then there's absolutely no relation whatsoever. So how can I certify by measuring the weight of a kilogram of a salt, certify the amount of
Okay. Is there a weight operator in quantum mechanics? Okay. Let me.
No, but the question is that
Okay.
but the question is that the P is undefined. I mean, the physical system has many different properties.
Okay. So look. So for me,
There must be some additional words which I am missing here.
yeah,
That the P
many.
are essentially
Okay. So for me,
physical
quantum measurements are.
It is meaning it's completely empty.
Okay, excuse me. Okay, let me finish. So for me, a quantum measurement is a resolution of the identity of a certain dimension into positive semi-definite operators, okay? I have told you what P is. It's just this, and this is just this. And I just want to have a definition of what it means for a specific P and specific F to have this relation. So I want to know what it means that F is capable.
F measure the same physical.
No, there's just an assumption that they are well-defined objects in the quantum formalism. Okay, anyway, operationally it's this, okay? So you have the real measurement for which,
They measure a physical.
excuse me,
Are we
I'm trying to give a talk here. Okay, thank you. No.
This is a seminar where I have to understand something.
Oh,
And,
well.
I mean, for the audience.
Or the audience, okay. I think the audience is fine. So there is a generic Okay. There is a generic pre-processing map. So this is just a quantum channel that takes my row into something which I can then feed into F. And I want that, first of all, this map does not depend on the input state, okay, because that will be cheating. It has to be generic. And you know, of course, it has to give me the same statistics, okay? And then this is essentially equivalent to saying, well, if I apply the dual of this map to my real operators, I have to get exactly the ideal operators, okay? Because if it has to work for every state, then it has to be like this, and now this dual is just a unital, completely positive map, okay? So this is just a mathematical formulation of what it means that F is capable of simulating P, okay? So this is for a single partite system, and of course it generalizes very easily to bipartite systems, where now I have two systems coming into P, and then I will do the same in case of F, but of course I want to kind of keep my product structure of the space, so I'm going to allow two pre-processing channels, okay? And I just require the same thing. And it turns out that this is actually, you can actually prove, you can use this formulation to show that measurements are what they are supposed to be. Yes, Wojtek.
Could you remind me this?
Yeah.
The more powerful device is if it's stronger wireless spelling quality, how you measure the powerfulness of the...
So okay, so look, so for now in this setup, I haven't really told you anything about violations yet, okay? So I think now I guess you should really think that.
I'm asking because you made the statement that F might be more powerful than ideal.
Yeah.
We want to try to see if it can simulate at least the powerfulness.
Yes, but okay, but no. So I made this comment just because if I give you an unknown box, and if you play with this box, and you realize, okay, this box can do something, then. Well, okay, you will find out that this box is capable of doing something, but you can never like prove, oh, this box is not capable of doing something else, okay? So in this sense, you cannot hope to say, well, this F is exactly P. You can only say, well, this F is at least as good as P, possibly better, okay? So this is just in the self-testing, you have to allow for this, okay? So, okay, so the certification scheme is actually very, very simple, okay? So we start with the same kind of entanglement swapping paradigm, except that now, okay, I have two states, tau 0 and tau 1, which are a priori unknown, and I have my unknown measurement, okay? And then if I want to make it device independent, or if I want to make a self-testing statement for this, well, I'm not quite happy with just receiving some states on Alice and Charlie. I have to measure these states, okay? So essentially, I add some more measurement devices which, accept inputs and give outputs, x, y, y, b. And essentially, it turns out that if the conditional probability distribution of a, b given x, y conditioned on a particular outcome of R maximally violates the right variant of CHSH, okay, then this F is capable of simulating Bell state measurement, okay? And just to recap, so remember that in the entanglement swapping, these were two perfect singlets, this was the Bell state measurement, and conditioned on a particular outcome, I had some perfect Bell state across the A and C boxes. Well, then it's maybe not so surprising that if I have a perfect Bell state, okay, maybe I don't know which one it is, okay? But nevertheless, I can always choose measurements such that the statistics will violate maybe not the original CHSH, but maybe some essentially permutation of it, okay? And what is kind of nice is that the choice of these measurements does not actually depend on this R. So Alice and Bob can kind of just do their measurements, and then only later they collect statistics, they find out the value of R, they compute the violations, and they can then deduce that F is capable of simulating the Bell state measurement. And the ideal case follows essentially from the rigidity of CHSH. It's actually very simple, and we can actually make it robust. So we managed to make it tolerate about 5% error. Of course, I haven't really told you what it means to robustly simulate some measurement, but we have a definition of that. And And we can also generalize it to bipartite measurements for which the eigenstates are not maximally entangled. So, you can imagine some basis which is composed not of maximally entangled states, but some partially entangled. We can also do that. We can also generalize it to tripartite measurements, where the middle box receive 3 different shares, and then using the Mermin inequality on the remaining boxes, we certify a measurement which is composed of GHZ eigenstates. And so, okay, so this just shows that, okay, you can do this. So you can really certify entangled measurements based only on the statistics. Okay, and the summary. So I've told you about self-testing today, and self-testing is really just characterizing quantum devices based on statistics alone. You can, in the usual setting, the most standard formulation, you just have a bell test and you certify states and measurements acting on it. And this can be made robust, so you can really apply it to real experimental data. Out of this, you can prove security of device-independent cryptography, which is kind of interesting from the practical point of view. And I guess the recent developments that we have seen recently on the archive is that, first of all, you can certify more complex objects. So not just states and measurements, you can actually certify, let's say, entangled measurements, you can certify quantum channels. So this weak self-testing, which I mentioned, shows that it's possible to certify a state without fully knowing the measurement, okay, which is also, let's say, kind of interesting. And maybe the last thing is that, you can also extend this notion of self-testing to prepare and measure scenarios. So instead of source distributing entanglement to Alice and Bob, you will just have Alice sending a state to Bob, okay, and then he does some measurements. And in these scenarios, you have to assume an upper bound on the dimension of your system. But if you do that, which is kind of commonly done in when studying quantum random access codes, it turns out that you can also prove an analog of a self-testing statement. And this is kind of interesting because this gives you some relation to mutually unbiased bases, okay? Because it's known that for some of these random access codes, mutually unbiased bases are the optimal measurements, and so this allows you to certify mutually unbiased bases in this setup. And if you're interested in this, you should come in 2 weeks because there's going to be a talk about this. Okay, and with this, I would like to thank you very much, and I'm happy to take any questions.
Questions?
I have a question to the audience. Who of you understand what does it mean CHSH? Who knows it? Look.
Yeah.
How much time would have you lost if instead of that you would write down everything? What does it mean?
For names. Just names.
Just names. You are not talking here to your colleagues working on the same subject, but to the broad audience, and we are not specialists. Just try to give us a chance to follow your...
I mean, I think I did.
Okay, thank you very much for this comment. Anyone else with questions? If not, let's thank Jędrzej once again.